Good afternoon, everyone, and thank you very much, Gina, for the invitation and for this very kind introduction. Really, it is always a pleasure for me to have the chance to talk about our work. In particular, this is a topic that I have very much enjoyed working on. Focused on this, how to use additive manufacturing to manufacture, to produce energy-efficient electric motors. Now, and in particular, we are going to focus in this talk about a very specific part of the motor, which is, I have here an example of this component, which is the rotor, which is a moving part, right? And you can see already here in this slide that the geometry is going to be very complex. So this adds challenges to the manufacturing of these parts. You can see from the last list of authors here that this is a fruit of a collaboration between different groups and different institutions in Europe. So besides IMDEA Materials, where I work, the Rey Juan Carlos University, University of Saarland, the National Institute for Metrology in Italy, in Torino, and also TU Berlin in Germany, and the company Heraus Amloy. We all, as I'm going to show later, but we are all partners in a project, this project here with the logo. We have the rotor logo here in our project, AM2 SoftMag, which is exactly about this topic. I want to start by going with you over this calculation. This is an estimation of the energy losses in electric motors in Europe. For me, when I first came across this calculation, I was really in shock because of the amount of losses. Now, so let us go through over this calculation. We have in Europe about 8 billion electric motors, and this is counting transport, but also industry, all motors, and they consume about 50% of all the EU electricity production. So this is a huge number. You have it here, 1,350 terawatts per hour. The number itself doesn't say much, but let us calculate the losses. So some motors, of course, are very, very efficient. We have an amount of losses of about 2%, but others have 25% losses. So if we take an optimistic average, this is about 5%. Let's assume 5%. This is optimistic. So all the energy that is generated, with the corresponding emissions to the atmosphere, that is distributed to each of these motors and that is then lost, is about 30% of all the electricity consumption in Spain. So these numbers are really huge. And this is what really motivated us to see what can we do. And we all know, especially this day and age, that energy is a very precious good. And this is very aligned with the mandate of the summit, COP28 summit in 2023, which there was this mandate to double energy efficiency by 2030. So we thought, okay, what can we do about this? And let's start from the beginning here. So let us start first by finding out what are the sources of energy losses in electric motors. I'm going to talk here or highlight only 3 out of the many sources. And well, I start with this image. This is a cartoon that I took from the internet. These electric motors are complex devices, and we are going to focus, like I said before, on the rotor. Is this part here. This is a moving part. It moves under the influence of rotating and dynamic magnetic fields, and is usually made of silicon steel in many cases. And I want to highlight 3 types of losses. The first one is eddy currents, which lead to the heat up of components. So in order to minimize or to mitigate this type of losses, we would need to replace silicon steel by a material that has a much higher electrical resistivity. Then a second source are magnetic losses, and this is because even though silicon steel is a soft magnet, still takes some energy to switch the magnetization. So in order to mitigate this type of losses, we would need an even better soft magnet, and we'll talk more later about that. And then there is a third source of losses, which are associated to the design of these parts. So with the current manufacturing methods, we cannot manufacture the complex geometries that would be required to guide optimally these magnetic fields. So we have these 3 types of losses, and what we propose for this project is that we can mitigate these losses by substituting silicon steel with iron-based metallic glasses. Metallic glasses, probably everyone knows, but they have very special properties because of their disordered nature. This is what I try to plot there. These are amorphous materials, and this lack of order endows them with very, very special properties. And we are going to talk now about these properties. I have to say we are focusing on this presentation on iron-based because of their soft magnetic behavior. We have, of course, metallic glasses that are titanium-based, aluminum-based, nickel-based, magnesium-based, and so on. But we are focusing on iron-based metallic glasses. And I want to also make Just open a parenthesis here to talk about the magnetic properties we are going to focus on. So I hope you can see it here. This is a hysteresis cycle. On the horizontal axis, we have H, which is the applied field. And on the vertical axis, we have the magnetization of this metal. So we have the typical hysteresis look. And the property we are going to be focusing on is HC. This is the coercivity. Of course, a very good soft magnet would have a very low coercivity, and then the area within this curve would be smaller, and the magnetic losses ultimately would be smaller. So this is what we are going to focus on. And I want you to take a look here to this graph on the left, where we plot the coercivity for different types of alloys. Here we have the silicon steels. And then here, within this darker orange domain, we have the iron-based wool metallic glass. Of course, there is a wide variety because we have many compositions that are possible and many ways of manufacturing them. But these materials in this fully amorphous state have the potential to have a very, very low coercivity and therefore to reduce the magnetic losses. But not only that, because of this disordered nature, they also have extremely high electrical resistivity. This is 3 times larger than that of silicon steels. So if we are able to use these materials to manufacture, for example, a rotor, we would also be simultaneously able to reduce eddy current losses. And also they have extraordinary hardness. Of course, structural properties are not the main focus of these components, but of course we always want components that are robust and that they can handle the stresses under operation. So at this point, you might be thinking, well, if these materials are so great, why are we not using them already? And the reason for this is that there is very large technological barriers to make large components with these materials, because in order to stabilize this amorphous structure, we need to cool them very fast from the liquid state. And the cooling rates that are required are of this order, 10 to the 4, 10 to the 6 degrees per second. This is extremely high and is not possible with most manufacturing methods that are available. It is possible, for example, using melt spinning. So we have here, for example, a container. This shaded area is the liquid metal. We apply a gas pressure, and then this liquid stream is ejected towards this rotating copper wheel. And in contact with this wheel, the material cools very, very fast. And then what we have is a ribbon, like the one you can see here. These ribbons are very thin, about 100, 200 microns. And therefore, yes, they are fully amorphous, because we are able to stabilize these disordered phases, but we cannot do much with them. So they have very, very niche applications. For example, they can be wound in some cases to make these transformer cores, but definitely we cannot make components. So we have here a set of extraordinary materials that we can, unfortunately, not use. There was a window of hope for the use of these materials when additive manufacturing techniques start to become more popular, more investigated. This is probably you all know, well, one of these techniques, laser powder bed fusion. So on the left, we have the powder deposit. On the right, we have the build platform. This platform at the beginning of the process is here on top. So we spread one layer of powders using this recoater, and the laser just melts, locally, following a pre-designed path, and this goes layer by layer. So there are 2 very interesting features of this process, laser powder bed fusion. I'm going to focus only on laser powder bed fusion in this presentation. But there's 2 important characteristics that are very relevant for metallic glasses. One is that because the laser is melting and a very, very small amount of volume of material, the cooling rates are extremely fast. So the range is 10 to the 5, 10 to the 8. So this exactly covers the range that we need to stabilize in situ the metallic glasses. And the other thing is because, we have a layer by layer process, we can make, as you know, these very complex geometries, and we can therefore also optimize and reduce the losses due to the component design. So this looked like a perfect match, but at the point where we started this project, this was in 2022, it had not been possible to manufacture fully amorphous iron-based metallic glass components with this complex geometry. There were defects, the lamination, the material would crystallize during the process. It was not possible. There were many problems. So we are going to see what can we do about that. We were searching for a breakthrough, and our target was, or our goal was even I would say, more difficult because we were not satisfied with just printing any iron-based bull metallic glass. We wanted a composition that had no rare earths because, of all the supply problems, no cobalt because of the social impact, and no phosphorus because phosphorus is very volatile and then you cannot control the composition and so on. So we wanted to get one of these alloys, and these alloys are extra complex because they have a very, very small glass forminability. Glass forminability means that even if I take this certain composition in the liquid state, I cool it down very, very fast at the right cooling rates, still I can only produce a certain thickness of material in amorphous form, let's say, and for these materials, this thickness is like about 100, 120 microns. Now, this is very, very small. There are other iron-based metallic glasses that can be produced with thicknesses of a couple of millimeters and so on, but these ones, with these compositions, the glass forminability is extremely low. And then we not only want to make these complex geometry components, with this composition, but we want, of course, high density and fully amorphous state, so we can really use their excellence of magnetic behavior. So we were searching for this breakthrough, and then we applied for a project to the European Innovation Council. This was the call, Pathfinder Open Call, and then we were funded. This is the AM2 SoftMag project that I introduced before. So we started March 1st, 2022. The project is 4 years. We are about to finish now in 2026. So I'm happy that I can tell you now all the process, and all the progress that was made throughout the project. And we got quite a lot of funding, 3.5 million euro. Of course, I say we because this is a consortium. In fact, the coordinators were Ralph Busch and Isabella Galino at the University of Saarland. Now Isabella moved to TU Berlin. They are experts in the physical metallurgy of metallic glass. This is such a complex problem. We propose to tackle it from different perspectives. So some groups, this group in Saarland, we're going to do alloy design, optimize compositions. Their challenge was, can we increase the glass forminability without introducing any of these elements that we don't want? And then we partnered with Amazement, a Polish company selling atomizers and doing powder atomization. And we at IMDEA Materials, in parallel with this German company, Amloy, we're going to focus on LPBF process optimization. And then finally, we were partnering with INRIM, with a group of Paola Tiberto, who are experts in Torino, in Italy, in magnetic property measurement. So this was the multidisciplinary consortium that we set. We were together searching for a breakthrough, and I'm going to try to guide you through the different challenges we faced and we overcame. And I promise you there is some good news in the end. But bear with me. So we start from the beginning. At the beginning, the alloys we had, there were a few commercial alloys, and this is where we started. I'm going to focus, of course, on the work done by our group on process optimization. No? And we said, let's start from the beginning. We don't know how these materials are going to respond to LPBF. We are going to use simple scanning strategies at the beginning, meaning by simple, I mean this meander scanning strategy, so just going back and forth along the cross-section of the sample we are printing. So we started with a commercial alloy, which was Cuamet 6V2. This is the composition here. I have to tell you, it was very difficult to find a supplier because, of course, these materials, because of this low glass forminability, they almost don't have application. So it was very difficult to find someone that wanted to supply them in powder form. But we found a Japanese supplier, Admix. And here you can see the morphology of the powders. They are relatively spherical. This is the particle size distribution. D10 is about 12. This is in microns. Sorry, I forgot to put that. And D90 about 56 microns. So typical size ranges for LPBF. We use this machine. This is one of the 2 LPBF machines that we have available at IMDEA Materials. It's a Renishaw pulse laser machine. It has 1 laser in this case. And like I said, we first tried to fix some processing parameters, so a simple scanning strategy, this meander scanning strategy. We fixed a layer thickness of 30 microns. This is also standard, and a hatch distance. So this is the distance between 2 consecutive scan tracks of 80 microns. This is also very standard. And then, then we used our reducible volume platform that you can see here, because we said, okay, we are going to start printing simple geometry, small specimens, these cubes, which have 10 millimeters inside. So we fixed the parameters I just mentioned before, and then we explored the processability window by changing the scanning speed and the laser power over the ranges that you can see here. And I have divided this in two regions. This orange region was an area corresponding to relatively high powers where we couldn't even print cubes. So within this very large processing window, there was the lamination, as you can see there was excessive melting. It was impossible to even keep the shape of the curve. But within the low power region, yes, we could at least print cubes. And what I'm going to show you there is, well, we want to, of course, keep the shape, but we want to have a fully dense and also fully amorphous material. So how are we doing there? Let's start with the density. So here we have a color map showing the density with respect to the scan speed here and the power and the laser power, all within this low power region that I mentioned, the region where we are at least able to print the shape that we want. And we have here two bad news. The first bad news is that, well, no, not yet. Sorry, not yet. The bad news comes later. But what the news, of course, is that we are not printing a fully dense material. The maximum density here is close to 95%. It's about 93.7 or so. The lowest density here is more close in the 60s. And here I'm showing you two cross sections. These are two optical micrographs parallel to the build direction, which is the vertical here. This is the lowest. The material with the lowest density and the material with the highest density. And it is bad news that we are still, even in the conditions where we get the highest density, we still have quite a lot of cracks. So this is still there. But what about the amorphous fraction? So I'm showing you here a whole stack of XRD patterns. And there's just two key learnings from this very dense slide. One is that, well, the one in the bottom, this corresponds to the XRD pattern of a melt span ribbon with the same composition. We know these melt span ribbons are fully amorphous, and this peak here, very white peak at 45 degrees, this is the signature of this fully amorphous material. The second one, this corresponds to gas atomized powder of the same composition. We are still with Cuamet 6v2, this commercial alloy. Again, yes, gas atomization involves quite fast cooling rates. So we also have this relatively large peak. And all the other patterns that you can see there, they correspond to all these what we term KS samples. It doesn't matter. These are all the samples that are included within the region of the processability window where we could get nicely shaped cubes. And as you can see in all of them, we seem to have this white peak at 45 degrees, but very clearly we have crystalline peaks. So in all this window, with the commercial alloys, with the simple scanning strategy, we always get a composite material, an amorphous crystalline composite. It is impossible to make a fully amorphous material. And here is where I wanted to tell you some bad news, which is the following. If we take a look, we measure the amorphous fraction by calorimetry, DSC, and here you see a color map with these measurements. Now, again, what is the amorphous fraction obtained within this processability window of scan speed and laser power? And we see the maximum we achieve is 48%. This is very far from our target. Our target is 100%. No? So this is very far. And there is another aspect that was challenging, and it's what is indicated by these arrows. As you can see here, the amorphous fraction under these processing conditions increases when we increase the scan speed and we decrease the laser power. And if you look at the density map, this is the same density map I showed you before, the density changes in exactly the opposite way. So it increases when we increase the laser power and we decrease the scan speed. So here we have two magnitudes that we want to optimize simultaneously, and within our processability window, they just change exactly in opposite directions. No? So this is what we call this density amorphous fraction paradox, and this is something that we definitely need to overcome if we want to solve this challenge. But before that, I want to show you a little bit how do these composites, crystalline amorphous composites, look like. And this is just a representative sample within this window. They all look similar. This is an optical micrograph, again, a cross-section parallel to the build direction. And we have polished this surface and then etched it to reveal the crystalline regions. These dark brownish regions, these are the crystalline regions. If you look at the top layer here, you can see very well the melt pools. And you can see that these crystalline regions are located around the perimeter of the melt pools. If we zoom in a little bit using EBSD, in the same sample, Here on the left, we have an inverse pole figure map, and the colors correspond to the orientation of the build direction according to this color coding. So you can see, no, sorry, that's not the color code. This is the inverse pole figure. But you can see by the diversity of colors that we have a randomly oriented microstructure. The crystallites are equiaxed. The sizes are from about 3-4 microns and below. And here to the right, you see this is a phase map where most of it is red, meaning that most of it is iron silicon crystals. And there is only a minor fraction. I don't know if it can be seen. These green dots here, they correspond to a minor fraction of borides. But this is how our composite looks like. We also went further we zoomed in more by TM, and you can see here an image of the crystallites. Then the melt pool here would be here, the boundary of the melt pool, and here is the crystallites in the heat-affected zone surrounding the melt pool. Just one last note from this part is that we started working with this commercial alloy Cuamet 6V2. We tried other commercial alloys, like, for example, FineMet. FineMet is a very popular soft magnetic material, and we found exactly the same. So here I'm comparing already. First of all, this alloy could also only be processed within this low power region, very limited region, processed into the shapes that we want. And then if you compare the density and amorphous fraction maps within that region, again, you see these arrows pointing in different directions. So again, when we use simple scanning strategies like this meander strategy that I remind you here, and these commercial alloys, it was impossible to optimize simultaneously density and the amorphous fraction. But that's what we wanted. So I'll show you later how we did it. First, one last slide. Ultimately, what we want are good soft magnetic properties, because these metallic classes, iron-based, they have very high resistivity. So eddy current losses, this is something that the property is already there. But what we want is to decrease this coercive field. How are we doing there with these commercial alloys? Well, I'm plotting here the coercivity versus amorphous fraction. All these blue dots, these are the printed cubes under different conditions. And here in red, you see an amorphous ribbon. This is for Cuamet. An amorphous ribbon with the same composition. The coercivity for the amorphous ribbon is about 10 amperes per meter. And look, here we are still, no matter how much we change the processing conditions, at about 2,500. So we were still orders of magnitude away from our target. So what did we think about to solve this? Well, what we thought is we could use other scanning strategies. And in particular, we tried to use what we call time delays. Let me show you what we mean by time delays. So here, this is just a schematic. By the way, time delay, we just use T off to replace time delays. So this is just a schematic. This is a cross-section. Here you can see the laser moving using a meander scanning strategy. This is a no time delay, the regular meander scanning strategy. And what I mean by introducing time delays, and here I'm introducing increasing and longer time delays, this is a time where we shut off the laser at the end of one of these scan tracks. So we let the sample cool down a little bit. So, for example, well, if we don't have time delays, you see these areas, the corners, because the scan track length is shorter, then there will be more heat accumulation. The colors here, red means higher heat accumulation, blue, less heat accumulation. And if we introduce time delays slowly, the basal temperature of these layers decreases. And we hoped that by doing that, we can somehow remove or counteract this density amorphous fraction paradox. Let us see whether this is effective and to which extent. So I come back to the original processability window. Can time delays allow us to widen this processability window? Again, this was the area, the blue area, where we can print cubes, but we have the paradox, and we use the second machine that we have. This is a Renishaw 500. This is a multi-laser, and it's more versatile, so we can really manipulate the scan strategy more. That's why we use this one. And we thought, okay, let us see if we can now, using time delays, process the material in this region that was before forbidden. Because, we have high power, this is a high chance that we have higher density here. So we tried 4 conditions, groups that we call A, B, C, and D. A is this here in red with the the higher volumetric energy density, and dark blue here is the lowest volumetric energy density. So we fixed these 4 conditions, these 4 groups, and we added time delays between one is no time delay, this is the default value, to 300 milliseconds. So let us see what happened then. These are the groups. And that's time delays, and let us see what happened. First of all, the first question was, well, this order of magnitude of the time delays that we are adding, is this meaningful? Does this do anything? So we picked 1 processing conditions. This is representative of group A. And we thought, okay, as we are showing you here in the top row, let us manufacture this with first no time delay, default value, and with 300 milliseconds. This is the bottom row. And we are going to measure the infrared emission using a built-in photodiode. And this is what we see. So with no time delay, we knew it. No, we are in the orange domain. There is no stability. There's no dimensional stability. We cannot print. And here you have the emission maps for layers 46 and 66. We have, of course, this heat accumulation in the corners. Now, when we introduce this 300 milliseconds time delay, suddenly, yes, we can print a cube as we want, and you see that the emission decreases in the same layers, right? So this seemed that it could work, but what is important now is to check how are we doing in terms of density and amorphous fraction, of course. Let us start with the density. So here again, I'm showing you several optical micrographs of, again, cross-sections of the cubes printed parallel to the cross-section parallel to BD. And the different rows correspond to groups A, B, C, and D. The first column with no time delay and the second column with 300 milliseconds time delay. So we can already see that when we use D conditions, these are the low volumetric energy density conditions. If we, on top of that, cool the sample more, we introduce a lot of lack of fusion porosity. But in conditions B and C, qualitatively, it looks like the density even improves with the 300 milliseconds. So let us do this more quantitatively. And this is what I have here in this graph to the right. I plot the relative density versus the time delay. So you see that for groups B and C, the orange and light blue, again, the density, yes, increases with the time delay, and it remains relatively constant for group A. Let us see how we are doing in terms of amorphous fraction. We measure the amorphous fraction for all these samples by DSC, and this is what I'm plotting here. Amorphous fraction for all the groups versus time delay. And we see that, indeed, increasing the time delay leads to an increase of the amorphous fraction. Most of it takes place within the first 50 milliseconds, but again, there is still a small increase. However, look at the highest values that we are getting here, about 70%. So this is still, even though we are increasing, the change in the scan strategy leads to an improvement. We are here still in QAMET 6v2, but we are still 30% off from our target of getting a fully amorphous material. What about the density amorphous fraction paradox? Do we have some good news there? Well, this is what I'm plotting here. You see density versus amorphous fraction. For example, for group B, yes, we are able to overcome this density amorphous fraction paradox by introducing the time delays. Now both density and amorphous fraction change, in parallel directions. Let's say change simultaneously in the same, they are proportional, let's say. And then, well, even in conditions light blue, which is C, and also red, group A, at least the amorphous fraction increases without any changes or major changes in the density. So it seemed like introducing time delays was actually good, but with these commercial alloys, we are not doing well still in terms of the absolute values that we want. Just one final slide to show you what about the magnetic properties. So here I'm plotting the coercive field versus the delay time for all this group of samples. And of course, the coercive field decreases with the delay time because we are increasing the amorphous fraction, but still our target is 10 amperes per meter. We are still in 1000. Okay, so what can we do then? Let me go over this one. This is still coercivity. So then in parallel, we were learning about how to optimize processing, learning about the beneficial effect of time delays. And in parallel, our colleagues in Saarland were working on alloy design, as I showed you before. And at this time of the project, this is 2 years already into the project, so they came up with a composition. They were, after trying hundreds, literally, of compositions, they were able to define a composition which is, these are the elements. I cannot, the actual amounts are being patented right now, so they're still confidential. But by adding nickel, they were able to increase the glass formability from about 100, 120 microns to about 1 millimeter. And then we thought, okay, let us now use these newly developed alloys, apply what we learned about process optimization, and let us see if we can really reach the target. So this is what we did, and I'm going to show you then what happened. And this is where the news, the good news are coming. I promise you some good news in the end. So again, I come back to this processability window that you know very well. This was where we could print only using a simple scanning strategy, but we want to use to print these new alloys within this orange domain, because this is where we can get higher densities and better properties. The first question for me was, well, if these alloys are so great, now they have such a much larger glass formability, can we print them without time delays? And this is the first thing that we tried, yes. And this is what I'm showing you here. So almost within this orange window of processing parameters, irrespective of the position there, I'm showing you here just one set of processing conditions, 180 watts, 615 millimeters per second. And you see how the cubes look like when we print them with different time delays. No? So even for these excellent alloys with high glass formability, we still need time delays if we want to retain the shape within that domain. So we fixed a time delay of 50 milliseconds. And then we thought, okay, let us now fix this time and then expand in terms of scan speed and laser power. Let's explore. The first good news there was that we did get a little bit higher density. This was 98% at some point, from 90 to 98 within this relatively large window. Again, here you have a representative optical micrograph. I think this is the highest density sample. We still have some cracks, so we were not able to fully get rid of the cracks, and the crack density throughout this region is between 1 and 2%. Crack area fraction, measured from the optical micrograph, and this is 2D, so this is, we know there's limitations to this kind of measurements, but at least the density was looking better. What about the amorphous fraction? And what I'm showing you here is more an overall view of this whole stack of XRD patterns. They correspond, these S samples, these are the ones where we fix a time delay of 50 milliseconds and we change scan speed and laser power. This J series, these are the samples with a fixed set of power and scan speed, but increasing time delays from like 50 to 200. And these R values are samples produced using a time delay of 50, but double scan. I mean, what my message here, I know this is a lot of data, is that I would like you to compare these XRD patterns with the ones we were getting in the commercial alloys when we were using the simple scanning strategy. So now, even though for some conditions we didn't fully get rid of the crystalline peaks, but if you compare here, already by XRD, we can see that the crystalline fraction is much smaller. And for some conditions, they are completely amorphous, at least XRD amorphous. But we wanted to check that using other techniques. So I bring you back this optical micrograph of the QAMET process sample, the composite. We had these brown regions, crystalline regions. We did the same. We polished the sample. One of the cubes made from the new alloys. Sorry, we polished the sample the same way. We etched the surface, and this is what we get. At least within the resolution of this technique, we don't see any crystalline regions. We measured in all these samples with the new alloy, all these processing conditions, we measured the amorphous fraction by DSC. They were all higher than 95%. And we use also EBSD to check. And here is a representative map. It's completely black. So I always say that I spent all my career looking at, this investigating nice microstructures using EBSD. All I wanted in this project was to get black maps. And this is what we got. And here, I put you the image that I showed you before in QAMET 6v2, so you can see the big contrast. So it seemed that we were able to make quite a fully amorphous material. I'm going to jump into the nano indentation because I want to go and finish with the magnetic behavior. How are we doing in terms of coercivity? So our colleagues in Italy, again, measured by using the same technique, the VSM at room temperature, the hysteresis cycles for all these samples of the new alloy, using the corresponding time delays. And let me show you the orders of magnitude we are now. Here is coercivity, again in amperes per meter. And you see now that for all these points, for all these conditions, we are between 45 and 75. So I remind you that we were starting from 1,000 when we were using time delays in the commercial alloys. Now with the new alloys coupled with the time delays, with the sophisticated scanning strategies, we can really get close to the ribbon, which is 10 amperes per meter. We are still not there. The latest advances now, and we are still 6 months, we have still 6 months to work on this, and we are seeing that if we anneal these samples, using the appropriate conditions, we can still really reduce the coercive field, getting to levels that are very close to those of the ribbon. And then just one final slide. So for this series, if we plot the coercive field versus the porosity, we see there is some correlation here. So once we have a very large fraction of amorphous material, then other factors come into play that influence the coercive field that are masked, if you have lower amorphous fraction. And there's several areas where we can work and keep improving. And with that, I finish my talk. So just 3 conclusions. The idea is when we use simple scanning strategies, we always face this density amorphous fraction paradox, especially with the commercial alloys. If we introduce time delays, this helps to really, reverse this paradox. And then we need a combination of alloy design and these advanced scanning strategies. But with that, we can really make complex shape components with fully amorphous phases, and relatively high density, which is what we want. Of course, there is a lot of work still to be done, but there was, I think there was a major progress within this project. And this was the PhD thesis of Marco Rodriguez and Saumya Sadanan at IMDEA. And then, I want to thank also the funding, and I want to thank all of you for attending, and I'll be happy to answer any questions.